What is the similarities between you, the Eiffel Tower, and the planet Jupiter? All of them are made of matter. I know this is very silly, and you are thinking, what else could they be made of? Is there anything other than the matter in the universe? But wait, there is an evil twin of matter, the antimatter. In this video, you will know the complete story of antimatter, the history of its discovery, why it is so rare in the universe, and can we use it in the future as a source of energy? So enjoy the journey with me. I am Ramanuj and you are watching Slice of Science. Every substance we experience daily is made of microscopic particles called atom. Atom is made of more tiny particles called proton, neutron, and electron. Proton has positive charge, electron has negative charge, and neutron is neutral. But they are not alone. They have their evil twins. Electron has its mirror image named positron, which was the first discovered antimatter particle. Positron is a particle with same mass of electron but with opposite charge, that means positive. Proton has antiproton. I know the name is not as cool as positron, but Shakespeare said, "What's in a name?" So let's keep the name aside and focus on the characteristics. The antiproton has same mass of proton but has negative charge. Now I know what you are thinking right now. If neutron is neutral in charge, then what kind of charge an antineutron would be? Well, neutron has no charge, but it is made of more fundamental particles called quark, which has charge. In fact, not only neutron, the proton is also made of quarks. There are 6 types of quarks, namely top and bottom, up and down, and strange and charm. Protons and neutrons are made of only up and down quarks. The up and down quarks are charged particles, but they don't have integer charge like +1 or -1. Instead, they have fractional charge. Up quark has +2/3 charge and down quark has -1/3 charge. 2 up and 1 down quarks make a proton, and 1 up and 2 down quarks make a neutron. For every quark, there is also an antiquark, which has same mass but opposite charge. So an anti-up quark has -2/3 charge and an anti-down quark has +1/3 charge. As 2 up and 1 down quarks make proton, so 2 anti-up and 1 anti-down quarks make an antiproton. And since 2 downs and 1 up quarks make neutron, so 2 anti-downs and 1 anti-up quarks make an antineutron. Yet the charge of antineutron is still 0, but the constituent quarks are the mirror world counterparts of the quarks of neutron. The story of the discovery of first antimatter particle was as spectacular as the antimatter itself is. Let me take you to the early 20th century with the time machine of our mind. It was the time when modern physics had started to spread its wings. The science world had been shocked by a new kind of physics named quantum mechanics. In our day-to-day life, everything we experience follows Newton's classical mechanics. If you know all the preliminary conditions of a particle, you could predict its every move at every moment of time. But in the microscopic world of the atom, things are not that easy to predict. There, particle behaves like wave, and wave could also have particle nature. This is called quantum mechanics. In early 20th century, physicists discovered that electron, which was previously thought to be particle, had wave-like characteristics. In 1926, an Austrian physicist named Erwin Schrödinger discovered an equation which explained the quantum behavior of electron. But this equation could not explain the property of spin of the electron, which was previously known to the physicist. So a new quantum theory was in demand which could incorporate the property of spin. In 1928, a British physicist named Paul Dirac developed a theory which could be satisfied if an electron had both spin and either positive or negative energy. Take the equation x square minus 25 equal to 0. This is a quadratic equation. This equation has two solutions, plus 5 and minus 5. Dirac's equation was exactly like this. If you solve Dirac's equation, you will get a particle could have either positive or negative energy. But the problem is that we don't experience any negative energy in our daily life. Nature is very strict accountant. She audits her energy book so carefully that no energy could be vanished from her book. When you rub your hands together, you get warmth in your hand. The kinetic energy of your hands, which is the energy of the motion, is converted to heat energy. When you switch on the light, it glows. The electrical energy is converted to light energy. So no energy can be disappeared. It can be converted from one form to another form. So there is no possibility of negative energy. Then what does the negative energy solution for an electron mean? Dirac thought that there was definitely a particle with same mass of electron but with equal positive charge. He named it anti-electron. Now this was a very bold idea at that time because the particle picture was very simple back then. Atom was made of positive proton, negative electron, neutron was yet to be discovered but generally accepted by the physicist that it might exist. The days of new particles with fanciful names which would be discovered in a particle accelerator were still in far future. So there was no place for a new particle apart from neutron. Dirac's theory was not seriously taken by the physics community. Every talk that Dirac gave in the months following the publication of the theory, people would ask him jokingly, "Where is your anti-electron?" Eventually, Dirac was so annoyed that he attempted to prevent the people by telling them that since the proton is positive, the particle which was thought to be an anti-electron might be proton. But it was Robert Oppenheimer who saw the full potential of Dirac's equation. Yes, it was that Oppenheimer who had later become the tragic hero leading the infamous Manhattan Project to produce atom bomb. Oppenheimer pointed out that the particle could not be proton because Dirac said that a sufficient amount of energy in the form of gamma ray can produce electron and its positive counterpart from the vacuum. So if you apply this process in reverse, just like playing a video backward, the pair of particles would be disappeared again into gamma rays. So if the anti-electron were proton, the atoms would survive only as long it did not meet the electron. Once they meet, the atom would be vanished in a flash of light. So in that case, matter also would not exist. Dirac immediately recognized the power of the Oppenheimer's deduction. In September 1931, Dirac published his conclusion that the anti-electron would be a new kind of particle unknown to the experimental physicist. Now the stage was set for the experimental physicist. The world needed another brave genius like Dirac. Why I am telling this? Because in 1923, 5 years before Dirac had published his theory, an experimental physicist named Dimitris Kovetslins was investigating gamma rays. To make them visible, he was using a device called cloud chamber. Let's talk about this little bit. Cloud chamber was the first particle detector invented in early 19th century by a Scottish physicist named Charles Thomson Rees Wilson. The cloud chamber can make things visible which is invisible to naked eyes. It is a closed glass box with a warm top plate and ice cold bottom plate. Liquid alcohol is sprayed under the warm top plate. When the alcohol evaporates, the vapor approaches the bottom and they get condensed by cooling down by the cold bottom plate. So the upper part of the box contains gas and the lower part contains condensed alcohol molecule. When a charged particle passes through this closed atmosphere, it collides with some of the gas molecules and ionizes them by knocking the electrons off the atom. The condensed alcohol droplets clump together around the path of the particle and create a cloud-like pattern. This is exactly like the vapor trails of the jet aircrafts, which can remain several minutes in the sky. The trail of the particles is like the tire marks of the car. If you add magnetic field to the cloud chamber, it bends the charged particles to certain directions because magnet has an impact on electric charge. A camera is set on the top of the cloud chamber to take the photographs of the vapor trails. By analyzing the photographs of those cloudy paths, the physicist can understand what kind of particles they are. If the trail is thick, continued and straight, then it is a positively charged heavy particle like alpha particle. And if it is very thin, discontinued, then it is a lightweight, negatively charged particle like beta particle or electron. For the 20th century particle physicist, the cloud chamber was similar to that of the telescope to the astronomers, because the cloud chamber could make things visible which were beyond their normal vision. Skobetlin's result revealed something utterly unexpected. The result showed that the paths of some of the electrons curved the wrong way. This is the path of the electron, but this path is the opposite to the path of the negative electron, so it must be a positive particle. Now we know that he was seeing the positron, but no one anticipated about a positive electron back in 1923. So he ignored it. In 1930, a British experimental physicist named Carl David Anderson conducted a similar kind of experiment. He used a magnetic field 10 times stronger than Dimitri had used. With this more powerful setup, he discovered that the cosmic rays contained negative and positive particles in about equal numbers. By examining several examples of his findings, Anderson deduced that the cloud trails of those positive particles are very thin, so they cannot be heavy particles like proton. So they must be that positive electron. Anderson had understood that he found the treasure. In 1931, Anderson had enough evidences to go public. He published a photograph of one of his experiments in the journal Science Newsletter. The editor of the journal named the new particle as positron, and it has been known as such ever since. Look at the trail. You are watching the photo of the first discovered positron. Once the news of the discovery of the positron had spread out rapidly, the experimental physicists across the world started looking through their old photographs and found evidences of positron. If those people had enough courage to go public like Anderson, their names would have been associated with positron instead of Anderson. Among those tragic heroes, two were Irene Curie and Frederick Juliet. They were the daughter and the son-in-law of Marie Curie. They had already missed a Nobel Prize for being the first to produce neutron in 1932. They had mistaken the neutrons for gamma rays. Now they realized that they missed the positron too. With no surprise, in 1936, Anderson was awarded Nobel Prize for discovering positron. So Irene and Frederick missed another Nobel Prize. Okay, don't feel bad for them. They had already won Nobel Prize in 1935 for producing short-lived radioactive nucleus. But think about that. This genius couple could have won 6 Nobel Prizes together. But unfortunately, they got only 2. That's life for you. Though Dirac wrote his original equation for electron, it also implied the existence of the mirror world partners of proton and neutron. In fact, in 1931 paper, Dirac wrote that If this symmetry is really fundamental in nature, then it is possible to reverse the charge of any kind of particle. Within 1957, antiproton and antineutron were also discovered. What happens when matter and antimatter meet? Let me tell you, this is nothing but a death meet. When matter and its evil twin meet, they both get disappeared, leaving huge amount of energy. This is called annihilation. Electron and positron instantly annihilate like a flash of light, leaving gamma rays. The annihilation of proton and antiproton is not instantaneous. Instead, proton and its negative twin do a brief dance before entering into their fateful death twinning. The dance lasted as long as 1/100th of a second. When a proton and antiproton annihilate, they produce gamma rays and a short-lived particle called pion. Then these two are also gone, leaving more gamma rays. The annihilation process produces lot of energy. If you want to know the exact number, you have to use Einstein's famous equation E equal to mc square. This equation can convert mass into energy and vice versa. Here E is the energy, m is the mass, and c is the speed of light in vacuum. So if half gram of matter and half gram of antimatter annihilate, it could release 9 into 10 to the power 13 joule energy, which is equivalent to almost 21.4 kiloton of TNT explosion or 10 atom bombs. In short, an 1 gram of matter and antimatter package could destroy a small city. Now the question is, if only 1 gram of matter and antimatter can produce so much energy, then why are we not using the matter-antimatter mixture as fuel? Because although our universe is full of matter, it is almost impossible to find antimatter in our universe. So to use it, first you have to create it in the laboratory. Even if you create it, you cannot store it in an ordinary container made of normal matter. So for this, you need to build an engineering marvel. And to build that kind of lab, you need money, huge money. That is the reason why the cost of 1 gram of antimatter can dwarf the economy of any developed country. One estimation showed that the cost of 1 gram of antimatter is $62.5 trillion. I think it is pretty expensive for a substance which does not even matter. But why is antimatter so rare in the universe? To find the answer of this question, we need to go to the origin of our universe, the Big Bang. The theory says that at the time of the Big Bang, which is the creation of our universe, first only energy was created, and then from that energy, equal amount of matter and antimatter were created. Then the matter and antimatter were annihilated to create energy again. And then again, equal matter and antimatter were created. The process of creating matter and antimatter from the energy and vice versa continued. So ideally, there should not be any matter and antimatter left in the universe. But at the end of several conversions, matter somehow survived in comparison to antimatter. The scientists calculated that there are billion gamma rays for each matter particle. So they think for every billion matter, there were billion plus 1 antimatter particle. So those billion matter-antimatter pair was annihilated, leaving billion gamma rays. But that extra matter particle could not get its anti-world friend for death. So it survived. How mind-blowing is this, that every matter that exists in our universe, which include you, me, approximately 7.5 billion people of our planet, our Earth, and our Sun, and billions of other suns, our Milky Way galaxy, and billions of other galaxies, black hole, all those stuff were made from that 1 billionth of particle left in the universe. But why did that extra matter particle survive? That is the big mystery. It is speculated that the laws of our universe apply on matter and antimatter differently, which gave the matter slight advantage over antimatter. So you see, not only human parents have bias towards their favorite child, even the universe has bias over her favorite matter child. But what was that bias which gave birth to a whole universe? To find the answer of this question, a team of physicists is working in the European Nucleus Research Center named CERN. There they have built an engineering marvel named antimatter factory. It is literally a factory which can produce antimatter. In that lab, they create, store and study antihydrogen, which is composed of an antiproton and a positron. Hopefully they will succeed in future and solve the matter-antimatter asymmetry puzzle. Let me finish the video with one of my thoughts. What would happen if antimatter survived? Think about that. Does the antimatter particle have any so-called anti-characteristics? They are just opposite to the matter. Just because they lost the battle against matter, that's why we label them as anti. There is a possibility that there could be an universe where antimatter survived. So in our universe, what is matter to us is antimatter to that universe. History always favors the winners, whether it is human history or the history of universe. Thank you for giving me your valuable time. If you like this video, please share this video with your friends and family. Stay rational, stay scientific. Tata.